Hello, everyone. Now we have Dr. Armstrong Foundjem. He's an AI researcher at Polytechnique Montreal, and he's going to talk about leveraging OpenInfra and open source GenAI to address climate change. Just another reminder, it's a very small group right now, but if you're interested in the AI panel, it's back in this room at 5, and then we have the closing notes after that. So you can stay in here, but on to Dr. Armstrong.
Thank you so much. So thank you everyone for coming. I really want to present most of the technical aspect, and I'll try to demystify uh, the algorithmic aspect of AI to make it user-friendly and understandable. So most of the things, it's not working here. Okay, so in my research, we do this kind of work for certification of safety critical systems, where we are trying to make explainable trustworthiness of aircraft and other applications. So I'm trying to bring in some knowledge, how we could help or try to collaborate with open source ecosystems like OpenStack to bring generative AI or AI in general, and to combat one of the most critical aspects in the industry, which is climate change. So this work was published, it's a published work for this, what we are seeing. So OpenStack is not just a project, it's a community of communities, an ecosystem, which makes it ready for this kind of work and could lead the way for many other open source communities to benefit from. So we just see how the feedback loop can collect massive amounts of data, different types of data, not only the commits, but we have bug fixes, bug reports, emails with complaints, communications from the IRC channels, and many other types of data. This will give us enormous power to train models that could understand the communities uh, in depth. So when we are talking about combating climate change, I want us to understand the different aspects of whether we mean the carbon footprints, the energy, or sustainability in general. Sustainability has several dimensions. It's not just about the carbon footprints. It's about maintaining the community itself to sustain doing what it's supposed to do and how it has been doing it for a prolonged period of time, uninterrupted, even when there are external threats. So we will see at socio-technical dynamics how to balance the collaboration within the community for effective best practices, how that could promote resilience and some correlations with energy. We will I will not give enough results on this cyber threat on cybersecurity because it's a very long work on its own, but I will give a result of what we have done there. Now we will mention the economic aspect of how open source needs cooperation from industry and other donors to better structure its economic models for sustainability. So we should not only be talking about the community for quotes. We need sponsors to sustain that community also for its financial activities, which is quite important. And last, the energy consumption model, how we could reduce the carbon footprints through this socio-technical dimension that I mentioned. So in this talk, I will focus on the first and second aspect on that dimension to see how we could make OpenStack more sustainable. So when we look at this climate change that a lot of people are talking about, it is something we need to pay attention to and see how we could, as a community, understand the various dimensions that we could practice and encourage best practices that will attribute to a reduction in global warming. The next slide, okay. It's okay. So let us just mention some key metrics that we'll be using here. We should not pay a lot of attention if this thing looks strange a bit, but it's just to say that if we want to measure something, there are tons of parameters, tons of metrics out there. We need to select the proper types of metrics that will give us good results. For example, we are talking about the carbon footprints. There are already established relationships like equations or models and already values that have been studied. We just can use it at this time. The key point to understand here is that when we are talking about the power usage effectiveness, we want to see how the data center itself consumes power and what power, the percentage of power that the IT equipments are consuming in relationship with the entire infrastructure in general. And that gives us a value here that suggests between 1.1 and 1.4. It means your data center is doing quite well. These are something we should just keep in mind. The rest of it is just to tell us that when we talk about energy, we need to measure power that the equipments are consuming over a period of time. And I will suggest a prolonged period of time. We can't just measure power right now for some few seconds and we say we have energy, because the equation of energy depends on power and time. So they go hands in gloves. And when we have this, the rest is just to convert to see the amount of carbon footprints that our community is generating to the global climate change or greenhouse gas. If we understand that these things are already just like equations that we can plug in, collect that figures, we want to see the factors that contribute or attribute some values to this. Now there are a couple of methods to collect data that will help understand these carbon footprints. Within OpenStack, you have different projects. For example, the Ceilometer can collect data within the project or the clusters. We can use telemetric data and many other forms of data to understand the various resources, how they are distributed and using resources. There are also open source tools. For example, there is one Python package that I use for this experiment that I will show. You can use it to collect energy and the carbon footprint on real time. Now, just to talk about other metrics that we measured and saw that they are quite impressive to understand how the relationship they have with the energy consumption. We will see like the amount of commits per week, the number of pull requests, the change and the adding and delete of code change, context switching. Some people are working on so many other projects, switching context from one to another and things like that. It's an important indicator to know. The review load, not everyone is just contributing code. Some people still dedicate time also to review codes that have been contributed by others. The number of meetings that people make and how they switch context from those meetings as well. We have the communication channels like the mailing list, the IRC channel, and many others. There are people who work during the late night hours, and we know how that means for a cloud system. The weekend activities, and sometimes we can mine the discussions that is happening within these communication channels like the mailing list and the IRC channel. When we mine this, we can build models to understand the sentiments of the persons, if they were using harsh, angry tones and things, to understand the state of mind as they were developing. This will help us to build predictive models. For example, we see here, one of the key points that we want to help the community to do is to predict burnout and how we could prevent it before it happens. Because contributors at some point, when you take, for example, a contributor who is so valuable within the community, I know everyone is, by the way, but at some point in time, you are attending a lot of meetings, contributing time, you don't really have time to rest and how to manage your workload. This is not a sustainable behavior, even within that community. So these metal models help us to understand that we can track certain patterns of behavior of the general contributors to now see how the average person within that the community is performing, as opposed to those who have indicated, or the system have indicated that they have a high probability of resolving into burnout. Now the community can do something to address it before it happens. It is not all about knowing that these metrics exist, but sometimes we really need to see the relationship. For example, how will someone convince you that making contribution has something to do with energy consumption? How is a commit relates to increase or decrease in the consumption of energy? These are the kind of things that we want to discuss in detail. Just because you make a commit and send a pull request, there is a team that has to review it and merge it, and it spins up the CI/CD pipeline. Sometimes it will pass, sometimes it may not pass. It may retry, and then it passes or it fails. All those activities are consuming energy, and sometimes when a job fails, before it fails, it has gone through so many other sub-processes that we don't see. And those are the kind of things that really increase the power consumption. And the worst still, when a job is trying or retrying, spinning a lot. And then when we look at the log files, we see certain patterns that we understand. We learn them through this generative AI technique to see the patterns that were the hidden structure behind the data. Now, we will also mention that if your system is too open for attackers or bad actors to hack, they can spin up lots of clusters to be running, and then you will run out of resources and the system will fall. So we need to protect our system against cyber threats. That's also important for energy consumption. We have seen conditions where a bad actor will not seize your clusters, but might just spin up nodes to always be at a certain threshold. You will pay either high bills of your consumption in energy, or they will always deprive high priority workloads. So they will always be in that state of retrying. It's difficult to predict this kind of bad actors, but with generative AI or with AI in general, we have patterns that we have designed that can fetch them out so easily. The next thing, the transitions are slow a bit, but anyway, let's see. Sorry. Okay, like this? Okay, thank you. So, oh, sorry. I think it's moving now. Yeah. Okay. So, we want to look at how we approach this measure without interrupting the workflow of OpenStack in general. So agentic AI solutions is here to be is our friend, a better collaborator and a tool that we could leverage. There are so many types of models. A lot of people, when they hear AI this day, everyone is thinking about generative AI. Generative AI is just one class of AI system. We have many that have been in the market or in the industry, and many are still coming up. One of them that we use in this study is reinforcement learning. And we will also discuss other techniques that we use as I show some of the slides. The end point is we simulated developers' behavior and interaction with the system. Since these agents themselves are within that same system that we are working with or experimenting in, we want to see how their interactions could bring out certain hidden patterns of the behaviors and interaction of developers with their natural environment, which is OpenStack, and how they collaborate with the code base and with different other platforms within the ecosystem. Now, this reinforcement learning, basically, it's a kind of machine learning models. It starts by making initiatives. It can make a first move. Like if you can ask him to solve a problem, he will make a first move. It doesn't necessarily have to be good. If the first move is bad, you penalize it. So it learns not to make that mistake the next time because it has been penalized. If it performs a good action, you reward it. So this activity of rewarding and penalizing the agent makes it smart, learns how to avoid decisions that have been penalized and how to take decisions that are rewarding. That's the basic concept of reinforcement learning. There is much to that, but I will not go into that detail for now. Training the model in this aspect, we just want to highlight here, when we talk about AI, it is good we come back to the basics of our own human intelligence. How do we learn? From neuroscience and psychology, we know very well that between the age of 0 to 5, that is when the brain fully develops and captures, I could say, a good number, more than 90% of all the information you will ever need in your lifetime. After that age, you develop. Between 0 and 6, we could see a child at that age start recognizing faces, tracking objects. This tells us about recognizing faces. Does this tell us about a kind of model we know in AI? Facial recognition and object detection. The next phase is object permanence, the early problem solving, understanding the causal relationships. The third stage, between 12 and 24 months, the child start developing language ability. And we go further from 12 and above, the expression of that language. Then we move to the next aspect with symbolic representation. So think about language model, what we know today as large language model. It's actually between the 2 and 3 years old problems. It is not the AI. It is only language model. AI has to mimic human in all these different stages. Now, some people will tell you that large language model is crap, don't believe in it. They don't understand what AI is. So just to keep us in line, we have to understand the different aspect of AI, which language model is one of them. We have other techniques. I've mentioned discriminative AI. I've been in the world for so many years. Oh, just hold on, let me see. This thing is not moving. Okay. 1 second, please. Okay. So we will see the different types of learning and how we have learned from nature. In software engineering, we have been using a traditional technical rule base where regular expressions and this kind of thinking, if this condition is this, do this. If this threshold is above this, branch right or left. It's one form of learning, but it is not learning information from the data. So in this work, we used logs from Zool, as we could see it on the screen. We see jobs that are successful in green and those that fail in red. We now learn the patterns using generative AI, as we see in this script. We fine-tune the language model to understand the context of open source, of OpenStack code base. Now we could now run our model that we have calibrated for the energy. So as it is running all this experiment, it is computing the carbon footprints of every cluster and then sum it total. So we have a number. And in this task that you are seeing right now, I asked the model to present like a project manager who has no detailed knowledge of the code base, like being a software engineer, but this project manager wants to design a workflow. So the language model now presented an effective workflow that would effectively and uses energy efficiently as well. So the most important part of this research is what we are seeing right now. We use what is called SHARP and LLaMA to explain the decision that was taken by the model. which feature contributed what amount to the final decision. It is not enough to collect metrics. I have seen a lot of people collecting metrics and then making decisions interpreting it is crappy in most parts because they don't study the futures of those metrics to know which particular metrics is important in the general decisions they want to make. That is where explainable AI has a lot to play. In this context, we could now see which particular metrics we can focus on and which amount of percentage it voted for the final decision to be taken. We also have the line for the local interpretation of the model's decision. And then finally, using all those factors, we could now predict the burnout for OpenStack, and we saw that most of the developers, even those that are working extremely hard, are still far below the threshold. Even when we reduce the threshold to 0.5, many people will not still fall under that burnout category. We tested this on some other communities, and we saw that a lot of people were around 0.6, which is an indicator that they have to adjust their work culture. The rest of this is just to tell us the different parameters that were used for the energy consumption and how the distribution falls to understand the patterns. It's helpful for the model now to make this decision. Now that we understand that there are several factors or features that contributed for that model, we collected all these features on all the massive distributions that we have. We try to reduce them on a two-dimensional space to understand the different clusters of each node you see in this graph represent a cluster that is running. And we want to see how the energy was distributed across. The purple, green, blue, and yellow that you see was just the different subclusters that we could group. Now on the red, we now calculated the energy that each of these clusters was using. With this, we can now understand if the pattern is out of distribution, if it is an attacker or some workloads. Many other intelligent decisions can help OpenStack at this point or any other community to know if it is possible to spin more cluster or to distribute workloads across clusters that are less consuming energy. At the end of the day, we were able to optimize energy significantly. And then we showed the difference between the predicted energy and the real energy clusters of that platform. Thank you. Any question?
This is pretty amazing. I'm a little interested. How did you train the model on some of the CI data?
So what we did, I come back a little bit. At OpenStack, the Zool has, like the portal, they have log files. Let me see if I can go backward. In this code here, okay, in this code to my right here, there is a link that we use to train the model. So I just show one of these, but all the log files, we were able to collect the log files and pass them so that the model will learn the patterns of those log files. And based on what the model structured as the patterns, we could now use what the model have learned to write a code with help of the model to detect those patterns. So even a code that passed the build, the model still learns the pattern. And the different reasons of failure are not the same. There are different reasons of failures. So the model now can see a job that is spin and predict that this job will fail. And if you are running high priority load, it's better to kill that job before it fails. And then you see, because we have seen also patterns where the code review was good, every other build was good, but it fails. Which means something was lacking that the human developers could not see. And when it fails, they went back and realized that something was actually missing, either within the code review or some gating issue They had to fix it, now it passed. That is where AI plays a role, because AI uses massive amount of data, and then it sees hidden patterns that we cannot see. And that hidden pattern is what gives it that ability to learn. Okay.
I was just curious if the data for the feature impact study is available to use?
Yes, it's open source. Sharply and LLaMA is open source. Python libraries, you can use them.
And the data is available as well?
Yes, the data is just you can use it in any data. Let me just give an example. Suppose we are all here in this hall. We want to make a data set of humans. You put, let's say, on the columns, the different features like age, height, weight, many other demographics and everything. We may have like 20 features. So each role now will be the individual person like myself, you, and every other person. Now we want to predict certain outcome. Which of those features is quite significant for the final decision that we want to make? We hear about models with 6 billion parameters. Are all those 6 billion, or let's say 100 parameters, really important to make decision? I don't think so. That is why there are mechanisms in AI, like in machine learning, called dimensionality reduction. I use TXNI is one, PCA is other, many others, just to make sure that we want to reduce the number of features like age, like the height, like the weight, and many other, to use only those that are quite useful or have shown strong significance for the prediction. The rest, we don't care, we just discard them. That is one aspect where once we do the future engineering, we can now explain the decision based on the features that remains. Might be one of them is super important for the study, and the others were just supporting it. So all those things gives us explanation of the model's decision. Yeah. Okay.
Okay. Yeah, we got fun. Does the model scale out to multiple projects or new projects? So you trained it on data sets from CI logs of existing projects, right?
Yeah.
So if you were to add something that's completely new,
Okay.
would it understand and be able to predict based on that?
Yes, that's one of the reasons we use generative AI, because by definition, they have already seen massive amount of data. So what we are doing is not really training, but fine-tuning. We are now taking OpenStack data and said, okay, you have seen a lot of data, but this particular data that we want to make prediction on, this is the structure, learn the pattern in this structure. So if a new project within OpenStack comes in, it already have seen the pattern, it cannot make prediction on this new pattern. Because in machine learning, we have also what we call out-of-back distribution. And that is where most models sometimes can fail to make prediction when that distribution shift occurs. And then the model have been used to seeing one particular type of thing. I'll give example like the self-driving cars. It was tested in Australia. It has never seen a kangaroo. They never trained it on a situation where kangaroos are. It looks at the kangaroo and does not know what that is. And it crashes into it. Now that is out of distribution. But if you have enough data to train the model, it will see those hidden patterns. And if you give a new instant, that's in frames time, it will make decision. Because when you train a model, you don't train with all your data. You train, you keep portion of the data for evaluating the model, and you keep another portion for testing the model. Yeah. Oh yeah, I mean, there is no solid rule, but what people have used, sometimes they will use 70% for training, 15% for validation, and 15% for test. Some people will use 60, 20, 20. Some will use 80, 10, 10. But there's definitely more. Yeah, more for training, because it needs to see more. The more you train the model on data, it learns hidden patterns. When I talk about hidden pattern, what do I really mean? Take, for example, all of us here are right now in America, in LA, right? this is something that is common among us. Now, there are patterns that when you start looking at the cluster like the one I showed, you will start realizing that in your community, there are clusters of community that is built within that community. Some people get along so easily with other people, but you don't see that in the data. Those are hidden features. And once you learn those hidden features, you now become smart to make decisions. You can now say, oh, these people already get along so well. If we have to do this job looking for people that we can just leverage it to them. So those kind of decision facilitates, those kind of observation facilitate decision. But if you don't really know the hidden, because we humans, we don't see data and see those latent properties. So making decision based on them is difficult. That's where machine learning has the strength of helping our decision making. Yeah. Thank you so much.